Okay, we are live and we have like 1 minute to go before the official time, so we're just gonna wait and start in a second.
You want me to stop the live streaming? Hello?
All right, welcome everybody to the ISSTA 2020 session on regression testing. So we have 3 talks in the session, and the first one, and I'm gonna ask Wing to start sharing his screen, is a dependent test-aware regression testing technique. It's a collaborative effort, and Wing Lam is gonna give the talk.
Thanks for the introduction, Alex. Hello, everyone. Today, I'll be presenting my work on dependent test-aware regression testing techniques. My name is Wing. This work was done in collaboration with August and Reed from the University of Illinois, along with Sai from Google, Mike from University of Washington, and Tao from Peking University. So let's first take a look at what a flaky test is. A flaky test is essentially a test that passes and fails when you run it in the same test scenario. In this case, being the same version of code, the same configuration to run the tests, and so forth. One prominent type of flaky tests are order-dependent tests. Essentially, these are tests that are flaky only due to the order in which you run the tests. An example of an order-dependent test is shown here. This test is from an Apache project with over 6,000 stars on GitHub. Specifically, what these 2 tests are doing is that the first test with line 3, it's checking whether or not an instance of a class variable is already shut down. But the instance can actually be started and not shut down by some other tests, like the one at line 7. And so what happens when you run these 2 tests is that if you see the T1 and then T2 run, then both tests will pass. But if you by chance see T2 and then T1 run, then T1 will actually fail. So why is this a problem? Why do we care about these tests? Well, for one, it actually makes test outcomes inconsistent. And because of that, they may lead developers to manually debug some non-existent faults in their recent changes and waste their time and machine resources to rerun tests. They also affect regression testing algorithms. So again, with a simple example here of 3 tests, T1, T2, and T3 run in that order, we would see all 3 tests pass. With test prioritization, we may see T2, T1, and T3 as the order, and in this case, T1 fails, like the example we looked at before. In test selection, we may select only T3, and now T3 fails. And we may do test parallelization, where T3 gets put on its own machine, and again, we see T3 fail. In fact, from our previous work, we've actually even found that many existing work kind of assumes that there are no order-dependent tests, especially in work like test prioritization, test selection, test parallelization, and even test generation. Specifically, in papers from ISSTA and so forth, we see that about 87% of them assumes that there are no order-dependent tests without any justification. We also found that as a threat to validity, that 10% of them claim it in there, and that's it. And finally, there was about 3% that actually considered order-dependent tests. So now that we see that order-dependent tests can, in theory, affect these regression testing algorithms, the question is how much? So in order to help with this, we first help understand the impact of these order-dependent tests on these regression testing algorithms. And then we want to look into how one can actually make these algorithms dependent test aware. To help with this, we first perform a study on order-dependent tests and how they affect regression testing algorithms. We then present an approach to help enhance traditional regression testing algorithms so that they become dependent test aware. And finally, we perform an evaluation on 12 of the enhanced regression testing algorithms to see how they compare to the unenhanced ones. For our study, we first selected subjects from our previous work, which created a data set of flaky tests with GitHub projects from specifically 8 real-world ones. These 8 real-world projects in total contains about 3,300 human-written tests. With the popularity of automatically generated test suites, we also use Randoop, a state-of-the-art automatic test generation tool, to create over 18,000 automatically generated tests. From these human-written ones, we find that 111 of them are actually order-dependent. From the automatically generated tests, we find that about 28 of them are order-dependent. Although the number of order-dependent tests here might be kind of small relative to the entire test suite, it's important to understand that their impact can still be substantial, as we will show in the next few slides. So now let's look at one of the testing algorithms specifically, test prioritization. In test prioritization's case, we have a test execution order, and what test prioritization will do is it will give us a new test execution order. This order will help us achieve coverage faster and improve the fault detection rate. But one thing to note here is that the developer expects, no matter if they run it in the first, on the test execution order on the left-hand side or the right-hand side, they expect that each test should yield the same result. For test prioritization, we looked at 4 main algorithms, essentially ones that prioritize based on statements or methods, and ones that prioritize based on statements that haven't been covered, or statements just in the absolute number relative to the test. So overall, we find that there's about a 23% of the order-dependent tests that are human-written was actually manifest when we use test prioritization algorithms. One interesting thing to note here is that the not yet covered algorithms do tend to have more order-dependent tests than the other ones. Specifically, when we manually investigated some of these, we find that many of these order-dependent tests fail if one particular test is run before them. And in the not yet covered orders, generally that dependent test somehow happens to be in between the order-dependent tests, again, based on its coverage. Versus in the other orders, the dependent test was always running after the order-dependent test, and consequently, all the other ones, the other algorithms tend to have much lower number of tests that was found. Overall, we find that there's a modest chance for these order-dependent tests to affect these test prioritization algorithms, especially with these human-written tests. In terms of automatically generated tests, we do see that the change becomes quite a bit more drastic. In fact, we do see that it goes up to about 54% of the automatically generated tests that are order-dependent seems to have actually been revealed when we actually use test prioritization algorithms. Now let's switch to look at test selection instead. In test selection's case, you have a test execution order. And what test selection does, it gives you a subset of the test execution order to run. The idea here is that you can run them faster and get your results faster. Again, though, the developer's expectation here would be that no matter if I executed the entire test execution order or just a subset of it, each test should yield the same result. For test selection, we looked at 6 different algorithms. Ones that essentially consider statements versus methods, and ones that do some reordering versus ones that do no reordering. The ones that do reordering is essentially a combination of first doing test selection followed by test prioritization. In the case of test selection, we do see that it comes out to be about 24% of the order-dependent tests for human-written ones did get found when we actually used a test selection algorithm. One thing to note here is that these ordering algorithms do tend to actually have more order-dependent tests than the ones that do no reordering. So if you do happen to use test selection followed by test prioritization, it is especially important that you have a solution to help deal with these order-dependent tests. Overall, we find that there's a modest chance for order-dependent tests to affect these test selection algorithms, specifically for human-written tests. On the other hand, for automatically generated tests, we see that the test selection algorithms actually are rarely actually affected by order-dependent tests. In fact, we only saw one test that happened to have been selected for the different versions that we use for our subjects and was order-dependent for the automatically generated ones. Lastly, let's switch and take a look at test parallelization. In the case of test parallelization, you have a test execution order that all of its tests are essentially split across different machines and run on those different machines. The idea here is actually to reduce the test latency, the time it actually takes in order to get the final result for all the tests. Again, the developer's expectation here would be whether if I ran these tests on different machines or if I ran them on one machine in this one test execution order, they should all yield the same result. For test parallelization, we looked at two different algorithms. If you parallelize by test ID, which essentially is just parallelizing based on which machine has the least amount of tests, or if you parallelize by test execution time. So based on the last time you executed these tests, how long it took, you use that information to parallelize. Overall, we see that there is a low chance actually for these order-dependent tests to affect test parallelization. In fact, we only saw about 6 of them out of the 111. In terms of automatically generated tests, we see that number do go up quite a bit. Again, it's also because the results for parallelizing based on test execution time do seem to see quite a bit more order-dependent tests found because of the reordering that it can potentially do. Overall, we see that the impact of these order-dependent tests ranges quite a bit, but there are a number of them that do have modest to high impact chances. And the other thing that I would caution you on is that these order-dependent tests did affect all of the regression testing algorithms that we looked at least one of the modules that we studied. So now that we see that order-dependent tests can affect these regression testing algorithms quite a bit, one natural question is how can we actually enhance these traditional regression testing algorithms so that they can be dependent test aware and be less affected by these order-dependent tests? Essentially, before we jump into that though, I will say though that order-dependent tests do provide developers some benefit. Specifically, it helps developers run their tests faster. In fact, when we actually looked on these open source software on GitHub, searching for annotations and attributes that helps developers run tests in specific orderings, we find them to be used in almost 200K files on these open source software. We also see that there has been various tools in recent years to help developers automatically find these test dependencies. And so one natural question here is, how can we actually enhance these traditional regression testing algorithms with some of these known test dependencies from developers or tools so that they become dependent test aware? So to help with this issue, we propose a general approach to help enhance these regression testing algorithms. Our approach is largely in 2 main steps. The first one is we generate the unenhanced regression testing order. We then reorder and add tests to the existing order so that we can output an order that would respect all of the provided dependencies. The input to our approach is simply the metadata that you would have used for the unenhanced regression testing algorithms, the original order in which the tests would have run by default, and a set of test dependencies. And finally, with all this information, we would output an enhanced regression testing order that respects all of the input test dependencies. So here is, we can go over each step of the approach. As input, again, we take the metadata, the original order, and a set of test dependencies. Our first step is to use the metadata and the original order on the unenhanced regression testing algorithm to get an unenhanced order. Using that order and the test dependencies, we then provide that to the enhanced regression testing algorithm that would actually then use that information to finally output an enhanced regression testing order that respects all of the input test dependencies. So now that we've shared with you our approach, we want to share with you how this approach would actually perform when we looked at 12 different enhanced regression testing algorithms on the subjects that we talked about earlier in our study. Specifically, for our experimental setup, we largely care about 2 main metrics. The first metric is how effective our enhanced approach really is at actually producing order-dependent test failure. The second one is on the efficiency. So when we actually, in terms of test selection, test parallelization, we may actually have to add tests to those to the test selection orders and to the test parallelization orders. And because of that, it can actually make those orders slower. So we want to look at, for the time that these unenhanced orders would have taken to run, how does that compare to the enhanced ones? All of the versions that we select for our subjects must pass in an original order, and they must have some code changes in them. And for each of the subjects that we talked about earlier, we actually select up to about 10 different project versions for them. So what we do is that on the first version, we would actually compute all of the input. So this includes the metadata, the original order, and the test dependencies. The way we get the test dependencies is we use automated tools. For more details on how we use the automated tools and which ones we use, please see the paper for those details. Once we've computed the input, we then take those inputs and use them on the second version and the subsequent versions of this subject. Specifically for test prioritization and test parallelization, we use them on the second version, and we see how the metadata, original order, and test dependencies would perform with and without our approach for the regression testing orders. We then also use it for selection as well, where we would use it on all subsequent versions. So we would use it on the second version as well, along with all the subsequent versions, using the same metadata calculated on the first version. The reason we do it this way is that by doing this, we also want to show that if you calculate the metadata, original order, and test dependencies infrequently, they can still be useful for many versions down the line. Overall, in terms of the effectiveness of reducing order-dependent test failures, we see that for 16 actually of the 26 enhanced orders that we looked at here, that turns out to be about 62% of them, we can actually completely eliminate all order-dependent test failures. We also see that when you start combining these different types of tests and the modules together, the enhanced algorithms overall can reduce the number of order-dependent test failures by about 80%. In terms of the efficiency of these orders, again, because our enhanced approach can add tests to test selection and test parallelization orders, we can actually be slower sometimes. And we can see that by the positive numbers on this table. But what we also see, though, is that there are some cases where we actually have negative numbers. And this is very interesting because what this is saying is that because we added tests, we are actually running faster. And the reason for this is because when we investigated these cases, we find that the order-dependent test failures from the unenhanced algorithms actually would cause the order-dependent test to fail. And because of that, it actually slows down the runtime of the test because these order-dependent tests are waiting for some resource, perhaps. Overall, we find that the runtime slowdown of these unenhanced orders compared to the unenhanced ones is only about 1% slower across all types of tests for all of the modules. So in conclusion, we find that most of the existing regression testing work don't really account for test dependencies. And yet developers are writing them, and they can be obtained automatically with tools. Because of this, we want to understand the impact of these order-dependent tests on these regression testing algorithms and how one can actually make them dependent test aware to alleviate the impact of these order-dependent tests. We accomplished this by first performing a study to understand how order-dependent tests affect these algorithms. We then propose an approach to make regression testing algorithms dependent test aware. And finally, we show an evaluation of how our approach performs, showing that you can actually have substantially fewer order-dependent test failures while only being marginally slower. Thanks. I'll take any questions at this point.
Okay, thank you for the talk, and we're going to move to the questions right away because we only have a couple of minutes. So I'm going to start with the first one, which is, what if we remove those tests that are test order dependent? What is the impact on coverage fault detection capability?
So it's a great question in terms of its exact impact on fault detection capability. I don't know exactly, for this work, we didn't exactly measure any fault detection capability just because all the subjects we have, all the versions and such, all have one passing order. So they really don't have any faults. Any faults is kind of a flaky test failure, any failures that we encounter. But in terms of the impact of simply removing these tests, it's the same thing along the lines of removing flaky tests in general. And it's problematic largely because developers typically aren't willing to remove tests. They don't want to do that. Especially in the case of order-dependent tests, if you run them in specific ordering, they still have fault-finding capabilities. So simply removing them could make it so that you actually do encounter regressions later that you could have caught with these tests.
Okay, let's see. So the second question is from Elaine Wayuker. And wouldn't this depend a great deal on the application? For example, with DB applications, you would expect to see lots of order-dependent tests, and seeing that the order correctly is handled is important.
Yes, we didn't specifically look at how different categories of projects would affect the results here, but I do agree with you that there are definitely some that would definitely be more prone to it. In fact, the first one that I shared is about the Elastic job is about a job scheduler. So that obviously also had some impact. We also have some databases that are part of our subjects as well that are also obviously affected by these order-dependent tests.
Okay, so I guess we are out of time, so I'm not going to ask you the last question, but it's written, and so if you don't mind, responding on Slack, you can take it. There is the question by Lingmin Zhang.
Okay, thank you.
We thank you for the talk. Virtual applause, and we move to the second talk. And I want to remind the audience that you can post your questions on Slack on the channel for this specific session. Okay, the second talk is Differential Regression Testing for REST APIs by Patrice Gaufroy, Daniel Lehmann, and Marina Polishuk. And Daniel is going to give the talk.
All right, thanks a lot for the introduction. So as Alex said, I'm going to introduce you to differential regression testing for REST APIs. This is joint work with Patrice and Marina from Microsoft and myself at University of Stuttgart. So before I go into our approach, I first want to motivate why it is important to look at REST APIs and test them. And first, what are REST APIs used for? So typically, they provide you with a programmatic access to web services. And that could be for a mobile application, could be for scripting. But most importantly, and recently, they are used to access cloud services like Microsoft Azure or AWS. A typical REST API interaction is between a client and a server. And say the client requests some resource via HTTP. And then the server responds with structured data, like in this case, JSON. And then the client decides to modify some resource, for example, here with the HTTP put verb. So this model, or this model of REST APIs is very simple, and as such has been tremendously successful. And many services are available via REST APIs, and their capabilities have grown a lot over the time. So the number of endpoints, for example, in this Azure API that you can see on the lower right corner has increased dramatically over 3 years. And given this quick evolution of REST APIs, it is important to find regressions, because regressions, especially for cloud services, have caused very severe outages if they appear in their REST APIs. So how do we find regressions in REST APIs? And the first option is to do a staged rollout. So first you supply a REST API only to early adopter customers, and then you roll it out across a single region, and only finally you provide it to all customers of a global cloud. But that still has the problem that it only catches bugs after they have been introduced in production, which is clearly not desirable. So a better option is to do testing before rolling out. And manual testing is an option, but that's laborious, and many developers find that quite boring. So a better option is to do automated testing. And one such tool, for example, is Restler, and that works as most automated testing tools. You first generate some random input. So for example, an HTTP request. You send it to the program under test, so a REST API or service, and then you observe the behavior or the output of that program, and then an oracle decides whether that constitutes correct behavior or a bug. And for a 500 internal server error response, that's pretty damn sure a bug, and it shouldn't appear. But the problem is that the case is not always as clear. So say you get a 200 OK response back. Does it mean the service behaved correctly, or did the resource actually not exist and a 404 would have been more appropriate? It's not so easy to decide. So one option to solve this oracle problem is to use differential testing. And the general idea here is quite simple. You generate some random inputs, and instead of giving it to a single program, you give it to 2 programs, and then you compare their outputs against each other. And if they don't match up, then potentially you have a bug in one of the 2 programs. And for that to work, the 2 programs obviously have to be related in some form. So one very successful application of differential testing has been compiler testing, where, for example, one program is GCC and the other one is Clang. Now, another option, instead of comparing 2 different implementations against each other, is what we do here in regression testing, and that is comparing the output of 2 different program versions against each other. So the idea is that you generate inputs for an old version of the program, and then you give it to both the old program and the new program. And the expectation is if the new program is backwards compatible with respect to the old inputs, then it should behave the same on those inputs. And if not, then we have potentially found a regression. Now, before I apply this idea or explain how we apply this idea to REST APIs, I want to highlight a crucial difference between regular programs and REST APIs. And that is that a regular program has a single software component or a single update that's happening. So the program goes from version n to n+1. But for REST APIs, we actually have two software components. And the first one is the service itself. But the second one is a specification of the service. And the reason is that the service is often closed source and not available to developers. So in order to write clients against the service, they need to have a specification. And this could be written, for example, in OpenAPI or Swagger, as you can see here on the right. And then third-party developers can take that specification to write actual clients against the service. And now we, as API owners, have to make sure that there are no regressions in those two components when we update the service and when we publish the new specification. So as there are two components of REST APIs, the service and the specification, we observe that there's also two types of regressions that are introduced in REST APIs. And to give you examples for both types, first, let's talk about regressions in the service itself. And that could be, for example, when a service on a previous service version responded 200 OK on some request, and then a later version of the service on the exact same request now returns 400 bad requests, which is obviously a regression for clients. Or another type of service regression could be if a service returns an unexpected property, for example, in JSON data, and then clients might be unable to pass that new body and break in the process. A second type of regressions is regressions in the specification. And the idea here is not that the service stops working, but that by an update of the specification, third-party developers are hindered in implementing this new specification, or that some feature of the specification is removed. And one example could be that, for example, an endpoint or a particular request type is removed from the specification, and then clients or developers can no longer write a client with the features that they had previously in mind. Or another type of specification regression is if a request in the specification now requires a property that was previously optional. And then new clients are maybe unable to provide this required property. Now, we want to find those two types of regressions in REST APIs. And for that, we instantiate the differential regression testing idea from earlier to REST APIs. And what you can see here is, again, the two software components, so the service of an old version and the specification of an old version. And then what happens is the first component gets updated, namely the service gets upgraded and put online. And now this new service can, for example, supply new features or answer to new types of requests. And now the first differential testing part of our approach is comparing the two outputs of the two different service versions against each other, but on requests from the same old specification. And if there's a difference between them, then potentially found a regression in the service update. However, as we've seen earlier, there's a second component that can get updated, and that is the new specification version. So now we as an API owner want to make new features in the service available to third-party developers, and we publish this new specification. And now differential testing runs requests against the same service version, namely the new one, but once requests generated from the old specification version and once requests generated from the new specification version. And again, the idea is that that the output of the service should be the same, and otherwise we have found a regression in the specification update. Now, for this to make this process actually automated, we cannot really wait for third-party developers to write a client against the specification. So what we do is we employ Restler, that I've mentioned before, as an automated tool to generate requests from a specification. So what Restler does is it takes a specification in OpenAPI as input, and then it generates a sequence of requests. And then we can use Restler to generate requests from the old specification version, from the new specification version, and target respectively the new and old service version. Now, in this overview figure, we've only talked about a single pair of REST API versions, namely N and N+1. But in practice, for example, for Microsoft Azure services, we see that there's a multitude, N API versions. And for each API version, there's a specification and a matching service. And so in order for us to test all possible combinations, we have this N squared matrix. And what, for example, this test configuration, this cell here in the upper left corner means, is that we send requests generated from an old specification version, or from the specification version October 2018 to the matching service version. But the adjacent cell to the right means that we send those requests, the exact same requests, to newer services. And obviously the other way around doesn't make sense, because otherwise the service would have to handle requests that are not even specified for it. So that's why it's an upper triangular matrix. And then we basically have to run our approach for each these valid combinations of specification version and service version. But this is not differential testing yet, right? So one output here is one behavior of a specification version and a service version. But what we set out to do was differential testing, so comparing behavior. And for that, we need to compare two adjacent cells in this matrix. And that means, for example, if you compare the cell here on the left to the cell on the right, this corresponds to an update of the service, but we send the same requests, namely from the old specification version. But an edge or a pair in the vertical direction in this matrix corresponds to requests generated from the old specification and requests generated from the new specification sent to the new service version. And for our approach, we basically need to evaluate all potential combinations of test configuration pairs, and that again is O of n squared. And so just to recap, in this matrix, we basically have a two-step process. First, we run test configurations, that's basically cells in the matrix, and then we compare pairs of cells in this matrix to obtain differential test cases. Now, to compare the output or to compare two test configurations, we basically compare what we call network logs. That's the output of a single test case. And a network log is essentially a sequence of requests and response sequences. And we do a recursive comparison after abstracting away some unimportant or unnecessary details. So for example, there are some HTTP headers that are non-deterministic, like date or request IDs for debugging. Or there's also some identifiers that are only generated by the fuzzer and not actually relevant to regressions. Those are abstracted away. And a second point of our diffing is that when we compare network logs from different specification versions against each other, we have to employ a variant of our diffing that we call stateless. And we have to do that, for example, because a specification might introduce new request types or might reorder requests, and those should be ignored, those reorderings during comparison. For time reasons, I don't want to go into more detail here, but please have a look at the paper for that. So now we finally want to know if this actually works, this differential comparison and evaluating this, this matrix of specification and service versions. And for that, we have done an analysis of historical versions of Azure APIs. So in particular, we looked at a large set of APIs from Azure networking and DNS services. So they can be used to spawn firewalls or to create load balancers or configure IP addresses and so on. And the cool thing is that all their specifications of those services are publicly available on GitHub. So we could use them as input to Restler for generating requests. And then for all those APIs, we looked at 17 historical versions dating back until 2016 and up to 2019. And this is quite a large API service. So in total, the specifications span more than 4,000 files and more than 600,000 lines of Swagger API specifications. And then for each of those 17 API versions, we had this O of n squared matrix of test configurations. So we had to run requests in 159 different combinations of specification version against a new or equal service version. And running those test cases took about 3 days. And then after collecting all this data, we did our diffing. And in the resulting diffs, we found actually 14 regressions in this historical data. And the regressions were in 5 different APIs, which is good because we see that it applies not only to a single particular API. What we also found is that we saw both types of regressions. So we found some regressions in specifications and some regressions in the service itself. And I'll give a couple of examples in a bit. And then the third encouraging finding is that both diffing directions in this matrix are necessary to find the regressions. So 5 regressions were only found when we sent requests generated from different specifications to the same service version. And 9 regressions were found when we generated the same requests, but sent them to 2 different service versions. And overall, this was some manual effort, so about a week of manual effort, because we had to inspect 272 diffs of which most were small or empty. So to give you a better idea of what those regressions look like, I want to show you some examples. And the first one is an example of a specification regression. So what you see here on the left is an old specification from 2018-06. And on the right, you see the new updated specification, 2018-07. And what you see is that some parameter here in the body of the request got moved around. So here it got pulled up one level. And the problem is that if you send those two requests to the same service version, the old specification requests return 200 OK, but the new ones return a 400 bad request. And we find that with our diffing, and that's clearly a regression. Now, in 1 month later, the specification was updated. And now the service returns 200 OK, which is good because we see that as a confirmation that this was actually a regression, and this was developers cared about it and fixed it. And then, interestingly enough, 2 months later, we see that this body of the specification of this body regressed again. And so basically going from October to November, we again send it to the same service version. And again, we get a 400 bad request from the new specification. Then again, this was fixed a month later. And I think especially this re-regression tells us that automated tooling is very necessary to find such regressions in specifications and services. The next example I want to show is again a specification regression. And what we saw here is that going from an old specification to a new specification, some endpoints, some REST API endpoints were just removed from the specification. And this is exactly a case where clients or developers that had developed clients against the old specification suddenly couldn't provide those features in the new clients derived from the new specification anymore. And in fact, in the public issue tracker, we found somebody to actually confirm this. This is a breaking change. And again, encouraging that we can find this kind of regression in a specification. And finally, I want to show an example of a service regression. So what we see here is the response body, JSON data, of a service of version February 2018. And on the right, we see the response of the service in April. And we have sent both services the same requests generated from the same specification version. And what we see here on the right is that the body contains a new property, which is not specified, and as such could break clients. And again, this is a regression that we could find with our approach. And with that, I'd like to conclude this talk and just give a short recap. So I introduced this notion of differential regression testing for REST APIs, which is different from regular programs because we have two software components, the service itself and the specification, and they could be separately updated. And then we consequently have also two pairs of differential test cases that we need to do. Then second, I talked about this specification and service test configurations, as we call it, and that they span a matrix. And for doing differential tests, we have to compare pairs of these test configurations. Then I talked only briefly about the diffing between two test configurations. And finally, I showed some examples of regressions that we could find in widely deployed Azure APIs. And with that, I'm happy to take questions.
Thank you for the talk. And let's see, we don't have questions on Slack yet, so I'm going to break the ice and start by asking you one question. And so one thing that I was wondering, so you showed that I had the question, then you showed the example basically about the regression that was actually fixed. For how many of those did you find that they were fixed, and how many were still there, as far as you could say?
That's a good question. So I don't know it exactly off the top of my head. I think, so in total it was 14 regressions, and certainly more than half of them were fixed.
Okay.
I'm not exactly sure. So I have to look it up in the paper. But I think except for the last two regressions in the most recent versions at the time of testing, all were fixed. And I think that's attributed simply to the fact that we did this historical or analysis of historical data. And I think a more realistic scenario, but that is of course harder to evaluate, is to do it in production when you have not deployed a new version, but if you do it on kind of revisions during development. And I've been told that since my internship passed, this has been deployed and has been very successful. So,
all right, good. All right, thank you. There is a question from Mattia Fazzini, and the question is: can you tell us a bit about how do you reorder requests or responses?
So I think this question alludes to this diffing part and comparing network logs, and in particular this stateless diffing part. And I think the core part here is that we build equivalence classes of requests and responses. So in order to ignore the order of particular requests in the specification, we basically build equivalence classes of requests, so an endpoint and an HTTP verb, and a hash of the body that was sent, and the status code that is returned by the service. And then this comparison is not symmetric, so it matters whether you have on the left the old log or the new log. And the reason is that it's always okay if a 400 bad request response gets turned into a 200 okay response, but the other way is not okay. So I hope either we can follow up on that later if that didn't answer your question, or we can maybe have a look at the paper together.
Okay, so at this point we are at the end of the slot, so we're going to thank you for the interesting presentation, and we're going to move to the third talk of the session and the last talk of the session, which is entitled Empirically Revisiting and Enhancing IR-Based Test Case Prioritization. And the work is from Shangyan Peng, August Shi, and Lingming Zhang. And August is going to give the talk. And August, I don't know if you're muted or if you're getting started.
Sorry about that. I guess I was muted the whole time. Yes, thank you for the introduction. I'm August. I'm here to present our work empirically revisiting and enhancing IR-based test case prioritization. So this is a collaboration with my co-authors, Cheng Peng and Lingming Zhang. So at the time of this work, our affiliations are as kind of listed here, where Cheng and I were at the University of Illinois at Urbana-Champaign, and Lingming is at University of Texas at Dallas. Since as of now, affiliations have kind of shifted. Cheng has graduated, so he's at Google now. I'm also graduated. I'm going to be joining the University of Texas at Austin next semester. And Lingming's actually going to be moving to University of Illinois at Urbana-Champaign. So that's where you're going to find us now. All right, so let's jump into things. So hopefully you're convinced by talks in this session and by the keynote today that regression testing is a rather important part of the software development process. The idea is that there are these tests we want to run, and that after developers make a change, they want to rerun these tests after a change to check that the changes do not break any existing functionality. So if they see a test actually fails after the change, this test is kind of indicating to them that there is a bug in the change. They just now stop and then fix that before moving on. So the problem with this regression testing is that running all these tests is rather costly, especially when there's lots and lots of tests to run after every change. So for example, companies like Google and Facebook are reporting very high numbers in the number of tests that they have to run every day. So earlier today in the keynote, we talked about a way to address this problem of regression testing through test selection. But for this work, we're going to actually focus on a different way to improve regression testing through test case prioritization. Where the idea here is that we have a set of tests we want to run, but we kind of have an idea that these tests are not all exactly equal in terms of fault detection capability. For example, if we were to somehow know ahead of time that test T3 is better at detecting faults than the other tests, then after the change, we may want to then run test T3 first instead ahead of all the other tests. And of course, other tests can also be run in different orders based on some metric heuristic of how good they are at detecting bugs. And in particular, if T3 does indeed fail after this change, the developer can now go ahead and start debugging and trying to figure out what the bug is, even as all the other tests run. So sort of overlapping the inspection time with test running time. So unlike selection, though, we're not saving in terms of actual test run because we're going to run all the tests. But that does give us a bit of confidence in the fact that if we're going to run all the tests, we're not going to miss in not running a test that can help us detect the bug. So eventually, they'll all be run. Now, then the question then becomes, how should we actually prioritize the tests? What's the order we should run them in? So let's start with a couple more kind of relatively simple ways of how do we prioritize tests. For example, one way is we call quickest test first. Basically, we're going to reorder the tests based on their runtime. So run the test that runs the fastest first. After all, if the goal is to get the failures to happen earlier on, then if the failing tests would be the ones that run fast, then why not run them ahead of time and immediately start debugging as early as possible? And while it seems rather simple, it's actually been found to be a pretty strong baseline at prior work on test case prioritization. Another potential way is that we can look at the history of the tests and sort of how often they failed in the past. So tests that fail typically mean that they're quite good at detecting bugs. So presumably it can help us find more bugs in the future. So we might want to order the ones that fail more frequently first. And this scheme is actually kind of adopted as a configuration option inside Maven Surefire, which is the testing plugin for Maven projects. And it's actually investigated at companies as well, like at Google, trying to see the failure frequency. However, a lot of research, traditional research on test case prioritization focused on very coverage-based techniques. Kind of as we saw earlier in Wynn's talk, some coverage-based techniques would look at what the test, what statements or methods the tests cover, and then prioritize the ones that cover more, or if we already run some tests already, run the ones that cover more diversely or different statements or methods, with the hope that we'll eventually quickly cover all the entire space and basically cover, get all the bugs. And this way of doing coverage test case prioritization is typically rather change unaware, where the idea is that we spend this time collecting the coverage on one version and get like a nice order there, and then use that order for many versions in the future. Now, a bit more recently, there's been kind of proposed to do a test case prioritization in a different way, using the power of information retrieval. Now, in general information retrieval, IR, the goal is to rank a set of text documents based on the relevance to a provided query. So inputs would be the set of documents and a query, and they get fed into the IR model, whose job is then to rank documents, again, based on how close they are to the query provided. Now, what does this have to do with test case prioritization? Well, we can then substitute the tests that we want to prioritize for the text documents, and we can encode the change code as the query, which we feed both to the IR model, and then its job becomes then to rank the tests based on the relevance to the changes that just made. And this was explored in a paper, 2015, on how to adopt these methods for test case prioritization. And it's actually, unlike the coverage-based ones, most of them is that it's actually change aware, because we are literally feeding the changes into the model to figure out how tests are close to the changes. Just kind of illustrate in a quick example of how it might work. Here is actually a real code diff we saw in one of our subjects. It's a code diff in the class called array container. And there's another test in this project, test serialization here, that the IR model actually found to be quite related to this diff, particularly because it actually uses a lot of this array keyword and starts breaking down the terms inside this inside the source code. This sees array happen a lot. And of course, this matches the class itself. It's an array container. And also this class itself has the word array appear in it 51 times throughout the entire file. So basically the information retrieval model thinks that this test is very related to this array container because it's using array a lot. And so there should be some relationship. And you might think like it's rather simple in that fact that it's looking at the terms, its array shows up. But it's actually quite effective in this case, in the sense that this test indeed did fail after this change, and our model correctly tried to rank this one quite higher up than other tests that did not fail. So that's how kind of an IR-based test case prioritization works in a nutshell. But there are several questions about it that were not really evaluated in the past that we really want to know, and especially if we want to consider using it in our software. For example, when we look at these tests that we want to pass in, how should we represent these tests? What's the proper representation? How do we parse the test code? What are tokens we fit in? Like, what's the best representation we want to use for these tests? When we look at the change code, again, a similar question is how do we represent the change code as the form of the query we feed to the IR model, and in particular, almost also as how much context we should actually feed in these changes. Do we just look at the lines that are in the diff, or do we look at the line, how many lines above it, or do we consider the entire file of where the changes are? And finally, then for the model itself, what model we actually use, because there are several IR models that are used for various different purposes, but which ones are the best used for test case prioritization? And aside from these questions specific about IR-based test case prioritization, there are more questions actually pertaining to the evaluation of how do we properly evaluate test case prioritization. For example, how effective are they with respect to real test failures? Because lots of previous work on test case prioritization evaluated using seeded faults in mutants, as opposed to looking at as real software evolves and test failures that actually indicate bugs introduced in those changes. Also, the question of how effective are they with respect to time, because a lot of previous work focused on with the assumption that time per test is the same. So kind of focus on the order the tests come in when we kind of have an idea that test times do fluctuate, time does fluctuate between individual tests. And so we really need to evaluate all these factors if you want to, say, propose to use IR-based test case prioritization in real software evolution. So in particular, in this work, what we do is we collect the data set for the sake of IR-based test case prioritization, collecting real test failures from Travis CI, Travis continuous integration builds, and collecting the test code and diffs from open source projects on GitHub. We evaluate IR-based test case prioritization on this data set, where we try to figure out which of those different factors, like test codes, the test code parsing, or which model to use, are the most effective for test case prioritization, and also do comparison against other traditional test case prioritization techniques. Finally, we also propose a new hybrid technique as a means to try to improve upon the existing techniques. All right, so let's start within the data set that we want to collect. And what we actually need from this data set is that we're going to need tests, obviously. We're going to need the code diffs. We need what test failures for the sake of our evaluation, and the test times. And what's nice is that we can actually collect all this information based on the workflow that developers now typically follow in the open source, where they're having their projects hosted on GitHub and their GitHub repository. So every time they make a change, they'll then push to the repo, and we can look at the repo to look at what are the tests there and what are the actual code diffs in the change. Now, when they push the repo, this can trigger a job on Travis CI, which will then check out the changed code, run the tests on it, and output job logs, in which case we can parse these logs to get what are the exact test failures and how long each test time, how long it took to run each test. Now, the exact details of how we collect this information can be found in the paper. I won't have time to go over those here. But overall, we collected data for 123 Java projects, overall with almost 3,000 jobs with test failures, and our data set can be found at this link here. Now, another question is then how we're going to then evaluate test case prioritization compared to different orders that are produced by the different techniques. Unfortunately, traditional test case prioritization research has focused on some metrics that we can use. One of the most popular one is this average percentage faults detected, APFD. So people might recognize this formula, but basically it measures how quickly the test order, you order a test to detect all the faults that the test can detect. So this metric is again, it's very widely used. It was actually used in the previous work on IR-based test case prioritization. But it makes an assumption that the test times are essentially equal, because they just care about the order the tests come in. A bit more sophisticated metric is this APFDC, average percentage faults detected per cost, which does take time into account. So it really figures out how quickly you really get in terms of time to detect all the faults. So we're actually going to do using both metrics and to really compare the different techniques based on both metrics, and then also compare cross metrics to see, okay, this APFDC, which is simply more realistic, how is it compared to people using APFD from before? Now, you might note that these metrics I'm talking about are like faults detected, right? But we don't actually really have faults detected, but we have our test failures from our data set. There's no direct mapping from test failures to faults, which is not really a big problem from work from before, because they actually seeded the faults and the mutants. So they knew what tests detected exactly which faults and mutants, but we don't actually know that here. So for the rest of the evaluation that I'm going to show, we're going to then assume that each failure maps to its own unique fault. So we're kind of measuring average percentage failures detected. We do consider the other assumptions, like, for example, maybe all the failures map to the same fault. But I'm not going to have time to describe that here. The paper will have our evaluation with these other assumptions. So now describe the data set and the metrics we're going to use. Now we're going to describe what we're going to actually use them for. We're going to basically ask first, what are the best options for IR-based test case prioritization? Basically, those questions of what's the best model, how do we parse the test code or the changes, and also how does IR-based test case prioritization compare against other test case prioritization techniques? Now, I won't have time to talk about RQ1 in detail. The details can be found in our paper, but in a nutshell, what we found is that the best options are we want to parse with the tokenizer on the abstract index tree for both the test code and the changed code. For the changed code, we want to consider the entire file as the context. So basically, we're looking at the exact changed file. And the best model we found to be used is the BM25 model. So with these options, we'll be using it for this opt-IR, optimal IR test case prioritization technique that we'll be using for the rest of the evaluation. So we want to then compare this test case prioritization techniques against each other. So if I'm focusing on the opt-IR I mentioned earlier, QTF is the quickest test first one, historical, based on the historical failure frequency. And then these are 4 common coverage-based techniques for test case prioritization. And we see here that if we look at this plot, that plots the distribution of APFD scores across all projects for the different techniques. That opt-IR, the IR-based one, is quite high. It's higher than all the other ones. In fact, like it's the highest mean, it's got the highest median APFD score. This column and this table shows the statistics test we ran, a 2-key HSD test, which tries to cluster the scores, distribution of scores from each technique, and show like which of those are statistically significantly different from another, and kind of ranking them based on how much better one is above the other. So A is the best, and opt-IR indeed is in the group A. And this project columns, this number B best projects column here represents how many projects where the APFD score was the best for this technique. So it's had the most number for opt-IR as well. But coverage-based ones are also no slouch. They're also quite high as well. In fact, the statistics test found them to be in the same A group as the IR-based test technique. Now, this kind of really matches what was actually found in the prior work for IR-based test case prioritization, where their IR-based one was quite effective. It's also compared against the coverage-based one as well, but that was for APFD. Now, what happens when we consider APFDC when the test times are taken into account? And things have shifted a bit here. For example, the IR-based one is no longer the best technique. The best technique actually is that very simple technique of ranking the quickest test first. It's got the highest mean and median APFDC values. It's in that group A, and it's got the most number of projects where it's got the highest APFD score. So while the other techniques aren't that far behind, they're AB, which is kind of the second best between A and B, but it's not outperforming anymore. Even this simple technique, it's simple technique is outperforming the other ones, kind of suggesting us that while we spent all this work investigating these test case prioritization techniques like fancy IR-based models, but they're still not outbeating this simple one that just works them by the test time. So we really want to do better than the simple QTF. So this is where we start investigating what are some hybrid techniques we can use to enhance the existing techniques to get them closer in performance. So what we consider is then taking some existing techniques like the IR-based one with QTF and the hysterical failure frequency based model. And we want to then combine them up, combine the heuristics they use to order tests together to form 3 different types of hybrid techniques by the combo of pairs, and also one that tries to combine all 3 heuristics together to make kind of a big super hybrid technique. And when we evaluated these hybrid techniques, we indeed find that the hybrid techniques have higher APFDC scores than the single ones, suggesting that hybridizing really does help in this case. And indeed, when we combine all the heuristics together, we find that that provides the best relative group. It has the highest mean, median APFDC scores in that group A once more, and the most number of projects where it's the highest. So before I conclude, I really want to bring up a quick point about flaky tests, which, as you maybe recall from earlier in the session, that flaky tests are tests that non-deterministically pass or fail for the same code version. And particularly I want to bring it up is because it does raise a bit of a threat to validity for our study, because we are really relying on the test failures we observe from the real software evolution. And what that means for our study, is that if we have 2 orders proposed by 2 different test case prioritization techniques, one that ranks T1 higher and one that ranks T1 lower, if T1 happens to be the failing test, we might think that order 1 is better because it got the failing test up higher. But if I tell you that T1 is actually a flaky failure, then all bets are kind of off, that this comparison feels kind of wrong, that why should then order 1 be better if T1 is actually a flaky failure, not related to the change I just made. So we did looking at that, we tried to break down the jobs we had, where we try to get between flaky jobs and non-flaky jobs. Where flaky jobs are ones we rerun a number of times, and we found that the tests actually do pass fail, so they're flaky. While non-flaky jobs are ones that consistently fail the number of times we rerun them. So where they're not completely, we can't say for sure they're not flaky, but we're a bit more confident that they're not flaky. And this flag shows distribution of the APFDC scores across different techniques when we break them out between these 2 jobs. So we see some cases where, like for historical, based on purely on the failure frequency, that for the flaky test jobs, it seems to be better in terms of APFDC score, but much lower when we consider the fact only the non-flaky ones. So it's having an effect here. But for the hybrid techniques, we see that they're a bit more similar between flaky and non-flaky, and they also remain rather high there. So they're a bit, I guess, more robust compared to the flakiness. So to conclude, today I've talked about IR-based test case prioritization and several questions we have about how should we use it and how should we evaluate its effectiveness. And for this work, we present a data set for the sake of properly evaluating test case prioritization with real test failures and real software evolution. We compared a number of techniques with each other, but finding that the simple quickest test first technique actually outperforms all the other techniques. So we also explore evaluating hybrid techniques, finding that hybridizing does really help raise the APFDC scores. So our data set is actually available. You can try it out at this link, and I'd be very happy to take any questions now as well.
Okay, thank you, August. And so there is one question. We have like 1 minute, so we're gonna kind of fit the question in right away. The question is from Shoik Mondal, and I was just wondering how the formulation of APFDC will change if we executed test cases in parallel. On a different note, with the original formulation of APFD, does it take into account the impact of fault masking?
So for the first one about parallelization, I guess if you want to measure APFD, the metric will not directly apply there because I guess you are running multiple tests in parallel. I don't know how exactly on top of my head now how to really adapt it. One could run APFD or TFC on each different parallel machine and see how quickly you're on each one. I guess what you care about is that final time of how things go. I guess you'll have to really consider, yeah, if like sort of you start them at the same time, sort of this test goes to here and then it's going on the next test. Yeah, I'll have to think about it a bit more. Maybe we can discuss a bit offline about, or online later on about how we can adjust those. That's kind of interesting. For fault masking, I guess maybe if I understand correctly, this is the question of if I had run one test and it fails detecting the fault, if that failure actually prevents another test later on from detecting the fault. That's what I'm guessing it's the question is about. I guess in this case, the metrics themselves kind of assume that there is no fault masking, as in like if you know a test detects this fault, that then the moment it comes in, it will fail and detect that fault again. So I don't think they are prepared for this idea of like one failure masks another failure, which the test does not fail later on. So I guess that's another question. Maybe we have to reconsider the metrics as well to sort of adapt them to work better in this case.
Okay, so let's thank again August. So this concludes the session, and I want to thank everybody for attending, and thanks especially the presenter for giving